Good afternoon, everyone, and thanks for coming to this talk. My name is Stefano Zanero, and I'm an associate professor at Politecnico in Milan. And today, with my friend and colleague and former student Roberto Clapis, who is a security engineer at Secure Network SRL, a penetration testing company based here, we are going to kill or try to kill some zombies, some vulnerabilities that are coming back from the dead, and we don't know exactly why. So if you follow us during the talk, we will try to figure out which shotguns we can use to try and get rid of these zombies. These zombies in particular come out in a specific field of the current technologies, which is called IoT.
So we talk a lot about IoT, but without really knowing what's that about. So we took some examples of really weird IoT devices just to get you started. We saw that there was a smart hairbrush, which is connected to the internet. We didn't really figure out why, but it kind of gives you the health of your hair, which is very important to have out there exposed on the internet. And then there is a smart wine bottle that the bottle is smart, but the more you use it, you tend to get less smart. And at a certain point, it kind of becomes smarter than you, I think. Smart egg tray, this is beyond my understanding, and the smart salt shaker. This is incredible because it's about $200 to buy, and it doesn't actually grind any salt. It just gives you some salt and some ambient music while you eat. And this is the fun part, because I'm not actually going to buy those. But there are some more useful devices which you might want to buy, like smart wall plugs, so you can decide when a certain electrodomestic turns on or turns off. Smart keychain, so if you lose your keys, you're able to find them everywhere. And if someone is able to hack you, anyone else is able to find you and your keys. And a smart thermostat or a smart irrigation controller, which are kind of always been there, but you couldn't control them from your phone. So that's that. But then there is the scary part, which is, for example, cooperative robots, which are automated arms that are really incredibly precise, and they cooperate with humans in the same ambient. Those are not intended to stay in a cage like most robots. You're going to use them if you work in that field, and you're going to cooperate in the same space. So you don't want one of those things to punch you in the face when you less expect it to. And there is insulin pumps for diabetics or automotive. Every time you drive a car, mostly modern cars, you're probably going to have some part of it connected to the internet, or at least to a GPRS connector. And surgical robots. You don't want anything to have a blue screen while your heart is open beneath it. And this is why this is important. Problem is the threat modeling. Those things were most of the time not designed to stay on the internet. They were designed to stay in controlled, safe networks. But they are not, because now it's cool to connect everything to the internet, doesn't matter what it is. So they're out there. You see those small dots behind me? Those are things connected to the internet, not servers, not applications, not web servers. Those are things.
Those in particular are industrial control systems, so they are plants of some sort connected to the internet. You can go to showdown.io and plot whatever map you want of the world and whatever is connected to it.
So those might be safety critical, and they are out there. And they might contain your personal information. So, with this, since our work is penetration testing and code review, and I mostly do code review, I'm used to look into the code and see what's behind that dot, what runs behind it. So, let's get into it, and let's talk about why we call them zombie vulnerabilities. Point is, this code behind me is plain C. I removed the not important part. And I actually laughed when I got at this point in code, because you can see an SN printf used below a comment that says, this is going to print the required string into the destination. The problem is that they didn't use a %s format string to copy the buffer. They used the plain buffer, which means that anyone that could connect to this device and send a %x or %n could take control of the device. This is a thermostat, so not that important, but still, this vulnerability is so old. It's like 1980s, something like that.
Yeah, it's a zombie coming out of the grave.
And this is something that really punched me in the face. It was like seeing a hand coming out of the dirt and say, hello, I'm back. Because this is a plain buffer overflow. This thing right here reads character by character a file and puts it into a buffer. It counts the length here. It counts the length of the buffer, but never checks it back. So it just puts stuff at an address on which it has no control. So it just keeps writing, and the funnier part is that those lines of code could have been written with an fgets. Would have done the same thing, but without the vulnerability. So this was in a POS device. This is not stuff that should be supposed to handle your money, or at least so I think. And this is a small thing, because let's talk about something more dangerous, like a robot that weighs 1.5 tons.
Yeah, sometimes IoT devices are a bit larger. Your car is larger, and an industrial robot is larger. This is a 1.5 ton industrial robot arm that we penetration tested in our lab at Politecnico. If you're interested, I cannot go into the detail, but you can go and find the stuff on robosec.org. So the first thing that we found, you know, when you start using something, you open up the manual. That's the first thing that people do. Most engineers, at least.
You should do.
Yeah, you should. So this is the manual, and the manual says, oh yeah, and by the way, all the controllers, controller is the technical name of the robot, all the controllers have a default user called default user with a password, robotics. You cannot disable the user, you cannot change the password. And you're like, oh, it's 2017, not this again. And then you shot the zombie in the grave. Because you can actually disable this user from Robotware 6.04, which is like a version of Robotware that came out last year. But you can do it. It's not disabled by default as it should be. You can go there and disable it. And I let you guess how many robotics installers go there and disable it. Before that, and remember, these are robots. If they work, people do not change software on them. Whatever comes before that has that password and login built in that cannot be disabled. So then we started looking at other stuff, even if this was already pretty scary. And so robots are complex. They have multiple computers inside. And whenever you want to update software, whenever actually you reprogram the robot, the programming environment dumps the whole software on the robot to make sure that the whole chain of software is all at the same state as the one you use it to code, which is actually pretty good. It's a good idea. But there needs to be a way that the other components download this stuff, because you only connect to a single point in the robot. The way these other components download stuff is FTP. And
you mean secure FTP?
No, I mean FTP. And it's FTP, and then we said, oh, of course, that's the reason why there's a default user and default password, because this FTP shares the same authentication with the FTP facing outside, with the APIs exposed in REST from the robot. These robots have REST interfaces that you can use to code with them. So that's the reason. It's actually not the reason, because if you disable the user, this still works, and you wonder how does it work. And the reason why this works is that for the first 5 minutes that you turn on the robot, user authentication system is disabled. You can use any authentication, any login, any password, until 5 minutes after boot, the robot is completely open, inside and outside. So at that point, we said, well, how does this thing verify that whatever it's loading is actually a valid image? It doesn't. It doesn't verify a signature, which would be the proper thing to do, verify that the software comes from the factory. but it doesn't even verify that it's proper software. If you give it like a bunch of zeros, it will load in memory a bunch of zeros and start trying to execute it, which obviously does not really work, but it will still try. And the other thing that we noticed was that at some point during this exchange in FTP, there was this retrieval command. So it downloaded something from the robot called startup info. And we found what is actually a zombie matryoshka of vulnerabilities, because first it connects without a login and password, because the login and password is disabled inside and outside, so you can FTP from the outside during the first 5 minutes of the life of the robot, and you can actually do whatever else you want. Second, there is this thing that can download things from /command/, which is actually pulling information from the robot, but also put things in /command/command, and it's like a bash file that is executed by the robot. And in that bash file, there is another thing that is called shell. If you do shell something, the robot picks up the command, and whatever is beyond shell is executing on the underlying operating system of which is hosting the FTP, which is another enormous why.
Wait, by which user is that executed?
Oh, there's only one user there, the administrative user.
Okay.
So, and finally, we looked at the code because, of course, the FTP server is not a standard FTP server because, you know, FTP is such a new protocol that you need to rewrite your own FTP server from scratch. And they rewrote it, and we never got any source because this was a test that we did, well, shall we say, of our own initiative on a robot that we had. So this is decompiled code. The most proficient of you with decompilation will notice that they didn't even manage to strip the symbols from the code, so you can decompile everything on the robot and actually read it as if it were source code. So this has not been edited. This is how it came out of IDA, the compiler. It came out this way. And inside, I just cut the lines that I couldn't show on the slide. Inside, there's this string. Oh, whoops. There's this string compare, which is the one interpreting those commands over there, which then has printfs. In this case, there is a %s, so it's fixed that you are printing a string into another string, but there's no check on the length. So there's a straight buffer overflow, like in the 90s, no question asked, and I felt young again. I felt young again, because this is exploiting like in the 90s. You were not even born in the 90s. So this is exploiting like in the 90s, and without any of the security measures that now we have in operating systems, beyond the security of the code, nowadays operating systems have resilience built in. It's not built in here. So here's my zombie vulnerability matryoshka. And then you think, well, these devices are not directly connected to the internet. Well, actually, according to Shodan, 28 of these robots are directly connected to the internet and reachable. But
let's not think about that too much.
No, let's avoid thinking about that. We can think about nuclear power plants afterwards. Most of the robots are behind things, firewalls, that are called industrial routers, technically. That's an example of them. It's not the one with the vulnerabilities because we didn't want to have it recognizable. So industrial routers are things that cost about 8,000 euros a piece, and they're supposed to keep the plant beyond them safe. We found 85,000 of these things on the internet with rough Shodan searches, 5,000 of which without passwords. So very safe. The ones with passwords expose, in any case, a web interface to the internet, in most cases. That's a piece of the web interface of one of these things. And if you can see it, it's a piece of PHP code which is already odd to find in a piece of hardware that costs 8,000 euros.
Let's remind for a moment that this is dedicated hardware running PHP.
Yeah, exactly. And it's basically just getting whatever variable you pass to it and slamming it into data and using it without checking anything. You can, it's not even fair. You cannot even say which vulnerability this has. It has all vulnerabilities in the same line of code. And when we looked at this, it was so awful that it needed to have an explanation. And the explanation was simple. Whoever wrote this copy-pasted code from this page from 2009, how to create an I obfuscated the name of whatever, because otherwise you can find the page, API with PHP, and the logo of the website is Create APIs the Easy Way. This thing was in 2009. The people that wrote the web page pulled it from the internet for shame. In fact, we found it on the Wayback Machine. But this thing is inside routers that cost €1,000 a piece. So, and that's so this is copy pasta, right? This is copy pasta, and then you see the zombie harm coming out of the pasta code. By the way, none of these graphics have been designed for the presentation. They are actually available on the internet. So there was already somebody that designed an icon with a zombie arm coming out of a pasta dish. I don't know why.
But you can actually buy the zombie matryoshka, I think.
Yes, the zombie matryoshka is actually a product. You can buy it afterwards. So 1980s called, and they want their vulnerabilities back. Why do we still have these zombies around inside our device, inside our devices? Inside very precious devices sometimes. So it could not just be, oh, it's a cheap device and then the code written on it is being written without security. I mean, a robot costs €80,000, and it's a pretty costly piece of machinery, dedicated, and also sometimes downtime for robot factories run in the range of $20,000 per minute of downtime. So they are pretty precious pieces of machinery. So we started a brainstorming with a lot of colleagues in the security industry, but also developers. We interviewed embedded developers. We wanted to understand why these zombies came out and came back to bite us. And to find it out, we openly tweeted and said to colleagues in the security world, tell me what advice we can give to embedded developers to actually write more secure code. So we found a number of reasons why these vulnerabilities are still alive and they're coming back to bite us. The first reason is an astounding lack of awareness. I see that there's a lot of developers here that came to listen to a security talk. This means that you guys have some interest in security. And we, security professionals, tend to think that everybody has heard about buffer overflows. Because we have heard about it for the first time in the early 90s. We've been talking about buffer overflows for more than 20 years, and on our operating systems, there's no more buffer overflows to exploit. There are, but it's difficult. There shouldn't be. But when you talk to embedded developers, you find out that, so you have, I was talking with a good friend of mine that is a lead developer in one of the leading producers in the world of embedded-based code and SDKs. So his code is used by other people to write thousands and thousands of firmwares for devices. And when we were discussing buffer overflows, he had two reactions. The first reaction was not realizing why string copy without any checks was a wrong thing to do. And the second reaction was, oh, okay, I realize why that's a problem. But you know, my devices are not like websites. They are not internet-facing. They are microcode on controllers. So there's a lack of awareness because vulnerabilities are something that happens to others. They are concerned with safety, and they should be, but not with security. Then there's two contrasting issues. One is old code. In this room, everybody probably has heard or has said technical debt, referring to a code base. When we talk of technical debt, we computer engineers, we usually measure it in months. Years, there are decades of technical debt.
In this case, you probably can count the technical debt in my lifetimes.
Yes, in Roberto's. So there's old code bases, and there's very new code bases. Devices that need to be pushed out in 3, 4, 5 months. So there's market pressure on the new devices. There's old code on the old devices. And all of this with a security community, us, unable to offer usable solutions.
Yeah, mostly because if you want your smart hairbrush to be out in the market, it's going to be there in 2 weeks. That's not my problem, but it might be for someone else. So we started digging, and we started to find even worse parts of the story, because at least if the code is bad, you might rely on the operating system to help you and protect the executable. Every modern operating system does that, except for embedded systems. So there is no segmentation in memory. If you start writing in random memory embedded system, you're going to write it. Nothing is going to segfault you. You're going to write that memory like it's yours. And no SLR, which means stack, is normally randomized. In modern operating system, you cannot guess an address in the stack unless you have a memory leak. In this case, it's not a problem because you know it's already there, which is fine if you're an exploiter, less fine if you're using a robot. And then WX or X means some pages of the code of the memory are not supposed to be executable or are not supposed to be writable. So you cannot write something and then execute it in normal flows. That's not something you should be allowed to do. Instead, you're running on a toothbrush. In that case, you can because it's cool. And the most astonishing thing is that when we read the documentation for GCC ARM, we realized that even stack canaries were disabled by default until last month. So
yeah, which is absolutely astonishing because one, for each and single every other architecture except ARM, this is on by default. So if you have ever coded on any other architecture for anything security related, you just expect it to be enabled. Because, two, there's no reason on earth for it to be disabled. This is not a feature that consumes many amount of cycles of clock, in particular on ARM. This is not a feature that can disable any feature that you may need.
Yeah, and mostly on ARM, many functions wouldn't even need a stack canary. Most of the functions in ARM don't have the need for that protection. So we at least expected, and that was on us, that some tools were there to help developers. So we tried to put together a list of stuff that developers may use, and the community suggested us some of those. We realized they were not embeddable in current IDEs. To develop embedded systems, you need to use a dedicated environment, which does not rely on plugins and which does not read any standard format for linters or checkers. The lack of emulators and the lack of testing is very widespread, and also there are no safer library that you can use. Because if you're going to write something for x86 today, you can use a lot of safe libraries, safe languages, so many things that are there to help you protect your users. That's not the case for embedded. So we were out of ammo here. We could not suggest most things. And the community also told us to start asking our clients and the people we do penetration tests on to fuzz their code. But I don't know if anyone here has ever tried fuzzing a piece of code with AFL, which is one of the most famous fuzzer. It's hard. It's actually complex, and that's my job. So you can't expect any developer to start fuzzing their code because it requires time, it requires skill. You cannot ask them to change language. At a certain point in the discussion, we had to ask people to stop telling us that Rust and Go are out there and they might work for embedded system. We know that, we like them, but we can't tell someone to rewrite 2,000 lines of code in a week because the language is wrong. That's not something you can do. You could use a tool which is Address Sanitizer, which is a tool made by Google, to try and find address leaking, double freeze, except if you're writing for ARM, which in embedded systems is kind of widespread. So the only combination not available for that tool between operating system and architecture is Linux ARM, which is
basically the embedded systems community.
So someone even told us to let people choose their tools. So they told us to ask people who don't know anything about security to choose the right tool for them to do security, which is not something that made sense. Or in some cases even told us to perform intensive courses and teach people how to manage threat modeling and do that with each and every developer in the company.
Yeah, there was a number of people that suggested that you cannot write secure code without proper threat modeling, which is actually the case. It's actually correct. But it's not a suggestion that you can give a developer that is developing libraries for embedded. That's not in their mindset. That's not their job description. And until there is somebody that can do threat modeling for them, that's just not going to work. So if this is the best suggestion that we can give them, it's absolutely useless. It's just like using those unapplicable tools that you can see on the slides.
How do you even handle that?
I can't even.
And the fun part, because we are not there yet, is when people asked us to tell the developers to always assume that any input, I'm talking about stuff that runs on sensors, that any input is untrusted, which means memory checking, analyzing, reading in the proper way, assuming stuff that you cannot afford if you have 400 kilobytes of RAM. You cannot just do that. As much as you cannot apply langsec, which means writing a parser for every input you expect. One, because if you cannot write proper secure code, it's very likely that you cannot write a parser. And also because that requires time, that requires skill. And we don't want to tell people, in order to kill a zombie, you need a nuke, because that's true, but that's not necessary. We wanted a shotgun and a target. So we started digging a little bit more, and we tried to ignore the part where people told us that we should teach developers to always read the assembly output of their compilers, because that's just something that you cannot tell.
No, the scary part about that was that in this conversation, the person suggesting that was dead serious. Like, yeah, obviously, whenever you develop something and you compile it, then you should read the output in assembly, because, you know, the compiler may have screwed up with its optimization, your crypto code. So, of course, every time you check the output in assembly, then why do you use a compiler at all? Write it in assembly already.
Yeah, and also, he talked about crypto code, which also means why are you writing your own crypto? But let's leave it aside. The last suggestion, which is, I think, the less applicable one, is to patch the standard library and change its behavior. Like, that is not going to break anything, like, anywhere in your code. There is something that is not here, but that I saw recently in a code review, which was someone that found a problem in the code of his colleagues, and in order to fix the problem, he patched the kernel in order to close a port. Do not patch the kernel. That is something that should not be done in general. So we got to this point. We needed a shotgun, and we needed a target on the head of the zombies. And this is where you come in.
Yeah. You want to shoot them in the head. That's the way you keep zombies down. They keep coming back because you don't shoot them in the head. So how do we shoot these specific zombies in the head? Well, first of all, we need to give developers a shotgun. We cannot expect them to do complex things that even security people get wrong. So we need to give them safe libraries. At the moment, there's no safe libraries that are encompassing everything. But for instance, there are safe libraries for handling type safety or for handling integer expansions and truncation. Integer expansion and truncation leads to integer vulnerabilities. We have not shown any on these slides because they are more complex to show than the ones that we actually picked.
But not because they are not there.
But they are there. They are extensively there. Also, you may wish to give the developers checklists, things that they can follow. So, for instance, the NASA, at the JPL, has created a standard for writing C applications that they put on spacecraft. And, you know, it's kind of difficult to patch a spacecraft once it's launched, because it's kind of far away. So you want to get it right the first time. And if you want to get C code right the first time, You need to give people guidelines on how to write code that is as close as possible to be fail-safe. And believe it or not, these are guidelines that come from very far away because they have been written starting from the use of C for programming spacecraft, so in last 20 years or so. In those guidelines, there's security guidelines as well. Security is in there. In the JPL code or in MISRA C, which is a very typical set of guidelines for writing C and a subset of C, really, in order to make code safe, secure, and maintainable for embedded devices. They are already there. And these guidelines have been written with an embedded developer in mind, which is something that security people are just unable to relate with. Also, there are guidelines that are simple cheat sheets. They are the thing that you want to have when the zombie apocalypse is upon you, and you need to have just things to cross-check out in order to avoid the most basic vulnerabilities coming back from the grave.
Yeah, a deadline approaching looks a lot like a pack of zombies coming at you. So this is probably something that you're going to need.
And also, another typical source of vulnerabilities for embedded developers is reinventing the wheel. Let's leave alone our FTP server on the robot. But for instance, one of the mechanisms...
Or the fgets. The fgets.
The fgets, yes. But for instance, updates, software updates, firmware updates. Every device that goes on the market today needs to have an update function. There's no need to rewrite them because every time you write one, you will make a mistake. We need to have safe libraries that handle this part. There are already some. For instance, Mender is a safe library already developed and already scrutinized for doing this. And it can be embedded in most embedded code. So these are the ways to shoot these zombies in the head. We need also a tool chain or chainsaw in order to grind some code and figure out vulnerabilities. And this list of tools is nothing science fiction-like. Flow Finder and CPP check are things that you can run. There's no cost involved. They are very easy to run, well, reasonably easy to run. They give out output that is the output from which people like us find most vulnerabilities.
Yeah, most of the vulnerabilities we have shown you, and a lot of them that I found, are just generated by the first two. So it's quite easy. It's just a command line utility.
There's a lot of very low-hanging fruit. They're low-hanging so low that they are basically in the grave and coming out. So there's also more evolved solution, like side tools like Framacy, but they may be harder to integrate in a development tool chain for embedded systems. But the first two tools you can embed and integrate in any development framework that you're using. CLang Analyzer can also be a tool to find vulnerabilities. They are all tools that actually work on their own, and they find a lot of the things that we have shown in these slides. These tools will solve 90% of the problem and leave 10% of the problem for people like us to find.
That are funnier to find, so it also would make my work more interesting.
Yes. And finally, another thing that comes to zero cost is enabling the stack protector. Whenever you're compiling for ARM, look at your toolchain. There's a very good probability, unless it's super, super updated, that it's not enabling the stack protector by default. Do that. The problem is, of course, that this needs to be done at compile time, and we have like 15 years of software developed without this around there. So there's a lot of technical debt around there, but let's try to get rid of it. Also, there's a lot of us that, believe it or not, get to dig into the graves of ancient code. So whenever there is a zombie apocalypse, and actually in the case of Night of the Living Dead, the film starts in a graveyard, but whenever there's a zombie apocalypse, there's some fool that wanders in the graveyard. Now, if you need to enter the graveyard during the zombie apocalypse...
In the case, we are sorry for you.
We are very sorry for you, but at very least, you can try to follow a good battle plan. The first part of the battle plan is getting all of the documentation on what has happened before, because if vulnerabilities have been fixed, for instance, in the Git history or in the documentation of the project, it's very likely that there are other examples of the same vulnerabilities across the code base. You can check if the code has already tests. most of the older developed code for these things does not have tests. If it does not have tests, you cannot even patch it without breaking something else. So that's a thing that is actually helpful if you are entering the graveyard in the zombie apocalypse. You can lint the code. Linting the code is a very simple step, and it actually finds a lot of the vulnerabilities that we have shown today. Static analysis tool, the first two tools that we have, can be run on any code base, and they can help getting that code base up to speed.
Yeah, about that, one of the best static analysis tool that you can have is grep, because you look for fix me in the code, and you mostly find only vulnerabilities or bugs.
You see, they are laughing because they don't believe us. But if you look for fix me in the code, you will find vulnerabilities. Everybody laughs at me, but just go back to your graveyard, look through the graveyard, search for fix me to do and things like that, and you will find vulnerabilities aplenty.
Yeah, and you laugh now, but you would be surprised to know how many devices have a wrong updating system embedded. What was that? The wrong updating system, like really bad implemented. 7 devices out of 10.
Right. The test run on
smartwatches.
Smartwatches. Yeah.
Smartwatches are not updated correctly, and those came out in the last 2-3 years. So we're not talking about history of code. We're talking about history of vulnerabilities that are still there.
And another thing that you can do on any ancient code base is seek out any custom crypto implementation and kill it with fire. Killing with fire works with zombies as well. So that's one thing that you can do, and it will solve vulnerabilities. You don't even know that the vulnerabilities are there. But if you kill it with fire, you are for sure solving an amount of vulnerabilities that you cannot even believe.
Burn custom crypto.
Yes,
always.
Burn custom crypto, always. And don't be afraid of refactoring old code, because many vulnerabilities stay there because people are afraid of getting to tackle technical debt. But if we want to kill these particular zombies, we need to tackle with technical debt. We are almost done here. There's a list of books that you need to arm yourself with the Zombie Survival Guide. There's a list of books and presentations that we advise. You can download them after our talk when you get the slides. So keep calm. Aim for the head. We have vulnerabilities in IoT devices because A, developers lack awareness. We need to raise their awareness. But B, we need to give them tools. We need to give them shotguns. We don't need to give them, oh yes, run threat modeling. They don't want to run threat modeling. They want something that finds vulnerabilities. We have things. We need, as a community, to create more of those things. And we need also to develop processes that are actually compatible with embedded development. If we do these 3 things, which is just point, shoot, and aim for the head, we can get rid of all this horde of zombie vulnerabilities. Thank you very much for your attention.
Thank
you. If there
you.
are any questions.